I have to say, I love this week. Cytoskeleton always strikes me as being boring at first blush, and even though I've taught this class so many times, as the cytoskeleton week is approaching, I'm always like, oh, here we go, the cytoskeleton. But I love this material. Dynamic instability to me is just completely fascinating. I just recorded a video for that. Cell crawling is an amazing story. And then just as I thought perhaps the boring subject was coming up, we're going to talk about muscle contractions, which might be the most amazing part of the entire cytoskeleton story overall. In order to understand muscle contractions, however, we need to take one step back in simplicity and talk about the power stroke of myosin, because that's really what governs the muscle contraction. So let's do that first. And we're going to talk about myosin 1 in this case instead of myosin 2. Myosin 1 is a single myosin head and lever arm, and myosin 2, which is going to come up in a moment when we talk about muscle contractions, is actually bundled myosin. Myosin that's bundled in this kind of opposing way, so that's myosin 2. But we'll stick with myosin 1 because it's a single monomer and it's simpler, and again it has a lever arm and a head here. And that myosin really wouldn't be much use to us at all if it wasn't interacting with an actin. Actin is going to be the thing that the myosin is pulling, and in this case we're going to see how actin is being dragged from left to right through the motion of the myosin doing what it does as a motor protein. So myosin is going to move in the presence of energy, and by moving, that myosin is going to drag or push the actin. So let's go ahead and get started. So myosin actually moves actin and moves the cell by virtue of what is called the power stroke. And the power stroke breaks down into 3 major steps. And I've said them many times in the lecture, but it's bind, pull, release. And the analogy I use in the lecture video, I can't even spell release. The analogy I use is crew, is rowing. And even if you've never been in crew, even if you've never rowed a boat, you've certainly seen people row boats on TV and in movies and things like that. So think about it, right? Bind is dipping the oars into the water. Pull is rowing, is putting in the energy to pull back. And release is taking the oars out. So if you're trying to row to a specific destination, you got to dip your oars in, pull against the water, take your oars out, put them back in, pull against the water, take them out. That's bind, pull, release, bind, pull, release. And that's exactly what myosin is doing as well. Now, logically, when you think about rowing, bind, pull, release is the best way to think about the cycle, logically, because that's what you do when you row. But I'd like to change that just a little bit, and I'd like to reorder it as release, bind, pull. Now hopefully you can see that I haven't changed the order of anything, I've just changed where we start. So now it's oars out of the water, dip the oars back into the water, pull against the water, oars out, oars in, pull, oars out, oars in, pull. So it's the same exact idea, it's just starting at a different starting point. And here's why I want to change the starting point, because of the chemistry of all of this. So the release step occurs when ATP binds to the myosin. So when ATP binds, myosin lets go of actin, and it's essentially free myosin. Binding occurs when that myosin head, which is an inherent ATPase, cleaves that ATP, that is adenosine triphosphate, into ADP. But it cleaves it into ADP and the phosphate. So the phosphate is kept. So now we have ADP and the phosphate is bound. And that is the bind step of myosin. So that's when it binds once again to actin. The pull step occurs when the inorganic phosphate has been released. So only ADP is bound by the myosin head. Now this is clear, clutch here, this is key. So why we have pull at this step is because of how I tried to carefully draw the process right here. See, when that phosphate is maintained by myosin, it is actually in the way. That phosphate is buried in the crook of the lever arm, and it's keeping the lever arm in its open position. When that phosphate is released, not only does the phosphate float away, but that doorstop, if you will, is no longer forcing this lever arm to be in its open configuration. Now, there's two ways to draw this, one inaccurate way and one accurate way. The inaccurate way to draw this would be to say, well, now with the absence of the phosphate, the lever arm swings shut. No. Can't do that. Can't do that because this lever arm is actually adhered to some other cellular component. It can't move. Well, its end can't move, I should say. So the only other thing to happen, the only other way to make myosin spring shut here, is to keep the point of the lever arm attachment fixed, but myosin has now swung shut in the presence of only ADP. And if myosin has stayed bound to the actin and it shifted in the way that I just said, then that entire actin filament has been pulled to the right. So let's go back and do it one more time with these basics understood. So we have a point of attachment, we have the lever arm, and we have the myosin head. We'll start with it in its open configuration. We are not bound to actin at this point, so what is myosin bound to? Myosin is bound to ATP. That's the release form. Myosin, being an ATPase, cleaves that ATP, that triphosphate, into a diphosphate, but the third phosphate group is kept. It's just kept there in that orientation. This is the bind step. This is where actin becomes bound to the myosin head. Now, with the release of that phosphate, this is the pull portion of the mechanism, the lever arm swings shut. The distance between the lever arm and the myosin head is going to decrease. As the lever arm swings shut, the only thing that myosin head can do, move further down on its actin, that has dragged actin even further to the right. So release, bind, pull is ATP bound, ATP cleaved to ADP and inorganic phosphate, and then the phosphate released for pull. If we go back to the crew example, bind, pull, release, oars in, pull back, oars out, oars in, pull back, oars out, then oars in is ADP and phosphate. Pull is ADP alone. Oars out is ATP. And that's the way that we cycle through the power stroke. So that's how myosin 1 interacts with actin in general. Now, let's talk about a muscle contraction, which actually relies on the very same principles, except in a little bit more of a complicated way. So we'll draw two different things here, the starting point and the ending point. As I've already said, for myosin 2, we have the same kind of myosin that I described earlier, but they're bundled in this head out, lever arm in kind of fashion. And they are interacting with actin, as I'm drawing here, and this whole unit that I've just drawn is referred to as a sarcomere. And this is the basic subunit of a muscle fiber. This is the relaxed form. The contracted form of a sarcomere has the myosin bundles in the middle, just as before. But those myosin head groups have pulled all of that actin in, all of that actin has been pulled in, and that has resulted in contraction. See, up here, the sarcomere was this wide. But after the contraction, we've lost all of this width of the sarcomere. The muscle has gotten shorter. That's a muscle contraction, the shortening of muscle. So we're just basically drawing in the sarcomere by pulling on these actin filaments and having them drawn inside. So the question becomes, how do you get from relaxed to contracted? How do you shrink the width of a sarcomere? Well, you already know the answer. Out of order and randomly between all of these myosin head groups, you're having a cycle. You're having a bind, pull, release cycle. I use the example of a mosh pit and a crowd surfer in the lecture. I'm not sure if that's the best analogy in the world. But imagine all of these dozens, if not hundreds, of myosin heads out of sync and in a not coordinated way, going through bind, pull, release. Well, bind means bind to the purple actin. Pull means pull it inwards towards the center of the sarcomere. And release means let go so that you're ready to bind to the actin again and pull it in even more. So it's almost like, I might not have used this analogy in the lecture, but imagine a large group of people holding onto a very long rope, and they're trying to pull a boat into shore, a very heavy boat that's floating on the water. They're trying to pull it into shore. Now imagine all of those people said, okay, you know what? We're going to do this in a coordinated way. We're going to do bind, pull, release, but when I say go, we're all going to pull, and then we'll go through the cycle together. Ready? Go. Everyone pulls. Now everyone release. Everyone lets go of the rope, and there goes the boat, all the way into the ocean. Not a good strategy. The better strategy would be to do it in an uncoordinated way. Everybody on the rope is going through their own bind, pull, release cycle, so that as some people are binding or grabbing onto the rope, others are letting go and taking a break to get ready to bind again. That way hands are always on the rope at some point. And everyone is binding, pulling, and releasing in different orders. That's exactly what's happening in the sarcomere. Each myosin head is going through its own bind, pull, release cycle at its own rate, and therefore there are always myosin head groups engaged with the actin at some point and also being pulled in and all of that. So the bind, pull, release is going on asynchronously here in the sarcomere. And to put it back into the chemistry, well, the bind is the cleavage of ATP to ADP, but the phosphate is still kept. The pull is ADP alone, and the release is ATP. And so that's the chemistry of the bind, pull, release. Now you can imagine if you have a lot of sarcomeres in a row, making up a myofibril, and then the myofibrils make up muscle fibers, muscle cells. As each of these sarcomeres shrink, as each of these sarcomeres pull in and contract, that muscle length gets shorter and shorter, and you have a muscle contraction. So if you stick your arm out right now, and you take your palm and bring it towards your face, in other words, bend at the elbow, as though you're making like a stereotypical muscle man muscle, showing off your biceps, the reason why your arm is coming up to your face right now, the reason why your hand is being brought closer to your head, is because your bicep muscle has gotten shorter. That's the contraction. Now, that bicep muscle's gotten shorter because every single one of the millions and millions of sarcomeres has gotten shorter in those muscle fibers. What's allowed those sarcomeres to get shorter is myosin pulling on all these actins and making that sarcomere width, shorter. Now, what do you need in order to move muscle? You need energy. Energy in what form? ATP. Why do you need ATP to move muscle? Because that's how you get this bind, pull, release mechanism. And then when it comes time to straighten your arm, it's not the relaxation of the bicep that does that. It's the contraction of your tricep, the opposing muscle on the other side of your upper arm. So there, the sarcomeres in the tricep become shorter, and that pulls your arm open again. So pretty interesting stuff. A nice interplay between anatomy and physiology and cell and molecular biology here. Okay, so one more thing then to talk about on this topic before we can wrap it up, which is the movement of voluntary muscle. So when you stuck your arm out, and I hope you did do it, when you stuck your arm out a moment ago, and I said, okay, now bring it towards your head, you made a conscious decision and said, okay, I'm going to listen to Dr. M and do this doofy thing. I'm going to bring my arm to my head. And that was a voluntary muscle movement. So how do we get to voluntary movement of muscle? That's pretty interesting as well. So what we're going to do now is zero in on a single actin fiber of the sarcomere. And maybe we'll put like 2 head groups here of the of myosin 2, just so we have more than one, because it is a bundle. And we're going to do bind, pull, release in the presence of ATP. So one initial thought is that, well, maybe muscle movement is regulated by ATP availability, right? So if you take ATP away, muscles can't move, and if you leave ATP in there, muscles can move. So let's explore that for a second. If we take all of the ATP away from a muscle, all the muscle will have left would be the ADP from the previous bind, pull, release cycle. What form of myosin is the ADP bound form? Well, that's the bind form. That means in the absence of ATP, all of the myosins are stuck engaged with the actin. Those muscles are locked. They're immobile. They won't relax. And you're in this tense state. Not good. So let's not take ATP away, because the presence of ATP allows muscle to be relaxed and immobile. It allows the myosin head groups to let go of the actin, so we need ATP. So how do we regulate it? Well, we regulate it with these two additional proteins called tropomyosin and troponin. Now, tropomyosin blocks or competes with myosin for access to actin fibers. So tropomyosin would be here. So in the presence of tropomyosin, muscles cannot be contracted. So right now, if you're lying still because of the action of tropomyosin. Tropomyosin is keeping those myosin heads from engaging with the actin of the sarcomeres. In order to move, a second protein called troponin will pull and shift tropomyosin out of the way. So troponin will literally move tropomyosin out of the way so that now these myosin head groups have access to the actin. So troponin alleviates the inhibitory effects of tropomyosin. Well, when does troponin do that? Well, troponin does that when you decide you want to move your muscle. So when you put your arm out and you decide to bring your arm in, bring your hand to your head, troponin has moved tropomyosin out of the way so that your muscles can now engage and pull that arm to your head. So you're controlling troponin with your thoughts. Pretty cool, right? That sounds a little bit kind of new agey and metaphysical, though. So how are you controlling troponin through your thoughts? Well, troponin will get out of the way, or I should say troponin will move tropomyosin out of the way when the troponin is bound by calcium. So calcium-bound troponin moves tropomyosin out of the way, and free troponin doesn't do squat. In the absence of calcium, troponin doesn't do anything, and myosin is blocked. When calcium is around, troponin springs into action and moves tropomyosin out of the way. So what controls the presence of calcium, right? Now it seems like you're controlling calcium release with your thoughts, and you are. And in fact, that's probably the most direct way to say it. At this muscle fiber, there is a motor neuron. That motor neuron has its axon terminals innervating the muscle fiber itself. The other end, the dendritic end of the motor neuron, is hooked up one way or another to the central nervous system. And so when you think, I'd like to move my arm, that conscious thought in your brain is transmitted through your spinal column to motor neurons in your arm. Those motor neurons fire. And in firing, they release a chemical called acetylcholine. And that acetylcholine is sensed by the muscle fiber, and when acetylcholine is around, the muscle fiber releases its own internal stores of, you ready for it? Calcium. And that calcium interacts with troponin. Troponin moves tropomyosin out of the way. Myosin can then engage with the actin, and we bind, pull, release, bind, pull, release, bind, pull, release until we shorten the width of that sarcomere, and the muscle contracts. The thought is gone. The muscle fiber reabsorbs its internal stores of calcium and sequesters them away. Calcium-deprived troponin allows tropomyosin to move back in the way of myosin. Myosin can no longer interact with actin. The muscle can no longer be contracted, and the muscle is once again dormant or still. So pretty incredible stuff. Take-home messages from this, well, we covered a lot in this lecture, but it really comes down to bind, pull, release. ADP with phosphate, ADP alone, ATP. That's the cycle of a power stroke. Myosin grabs onto actin. It pulls the actin as the lever arm swings in the absence of the phosphate, and then it lets the actin go so it can grab on again and keep on pulling. That's one myosin, myosin 1 on actin. Get a bunch of those myosins and bundle them together, and you've got myosin 2. Slap that into the middle of a sarcomere, flank it with fibers of actin, and then as each of these myosins are binding, pulling, and releasing out of sequence, they're pulling the actin in, and shortening the width of the sarcomere. You do that in enough sarcomeres, and the width of the entire muscle fiber gets shorter. That's movement. That's muscle contraction. But we'd like to be able to control it in voluntary muscle. So we have tropomyosin that actually blocks actin and myosin from interacting, and troponin allows that block to occur unless calcium is around. If calcium is present, troponin moves tropomyosin out of the way so that myosin and actin can engage with one another for muscle contraction. Troponin can only do that in the presence of calcium that was released in response to a motor neuron firing right on the muscle, and that motor neuron fired because of your voluntary thought. And that's how we control muscle movement. Who said the cytoskeleton was boring? I never did.